which essentially was given by, we proved that is the trace of row density matrix times the operator of O. And we say that you can, the point is that you have to have O or row, both of them, in a specific order. Why we are doing that? Because we want to link the quantum, let's say, expectation value of an operator, which we discuss about, I think someone says about x squared, if I remember well. We want to discuss about how to link that to the probability distribution. And we say that classically, what we have something like this, which is D2 alpha, W of alpha, and then we have the operator of O. And
I have a question.
Yes.
You said that there has to be a specific order within that trace. I thought the trace was cyclic.
Trace, no. Trace is perfect. Is in any ways that you want to have it.
Okay.
It's absolutely not a problem. Now the point is that associated to rho, you define a probability distribution. With this probability distribution, we label it with let's say minus sigma. Okay. And associated to the operator, we have a specific order, which should be the opposite way. Then it is plus sigma. Okay. Sigma could be +1 for normal order. Sigma equal to 0 is for symmetric. I think we discussed properly what we mean by symmetric operator and a normal order and anti-normal order and symmetric one. Anti-normal order. All right. And we have given names. Look, since Kevin, you asked the question, I'm addressing to you. So look, associated to rho, we have a probability here, which rho defines what is going on with the state that you want to do the average over. And operator O also, you have a specific order for it. But order for the probability or quasi probability and order for the operator, they should be completely opposite. This is hidden in the duality of quantum mechanics. It's a little bit difficult to discuss about that right now, but when we work a little bit, you understand that it is easy. One is look like, having two dual space, and these dual space, they are conjugate of each other, and then you define them. So for W, we had different names. So we say that if W is +1 of alpha, in some books, by the way, including the book that currently you are working with, is our main source, since this is D2 alpha, remember alpha was a complex variable, right? It's a complex quantity. So it means that this integral is a two-dimensional integral. Okay. People, they can do it either in alpha R and alpha I, which the entire alpha is given by alpha real plus I alpha imaginary. Or some people, they prefer to work in the space of alpha and alpha star. Okay, this is all up to you, up really to your choice. Or even some people, they prefer to work in the absolute value of alpha e power of I theta alpha. You can work with the absolute value of alpha and theta alpha. Essentially here, that will be d alpha I d alpha r. If you look at the integral, and that one will be d alpha alpha d theta. For that one, I think it should be d alpha star with a coefficient. I don't remember really what's the coefficient. You can find it out. All right, so that's a reason that if you look at your book, W is labeled by alpha and alpha star. But here I will just label it by alpha, which I mean that alpha is real and a complex variable, okay, imaginary side as well. So W plus, I call it I call it I call it sorry, do I call it Hosimi? No, I call it yes, I call it Hosimi function, which is Q operator, Q representation. Hosimi function. Okay. W0 alpha, I call it W of alpha is Wigner function. W of -1 alpha, which is anti-Semitic one, I call it P of alpha, which is Glaube function. Okay. Glauber's Sudarshan function. This is the definition that we do have. Remember, the representation that you have it for Q is symmetric. You representation is normal order. Representation for Wigner is symmetric. Representation for P is anti-order. Okay, so that's all. And we know very well that when you work in the Hosimi function, you deal with Hosimi probability distribution, then the operators, they should be in anti-normal order. If you work with Glauber, Sudarshan representation, then the operator should be normal order. While when you deal with Wigner representation, then the operator is symmetric way. Okay. So that's a general situation, and I remember that we had a super operator of which we built up, and from the super operator we want to just prove the above relation, this relation that we had it here. So this was the goal that we want to create, and we want to prove that. So just review a little bit what we mean by super operator that we define. So we started with a displacement operator, which displacement of, let's call it alpha. And we say that the set of alpha, they are complete bases. And we know that you can have normal order, anti-normal order, or symmetric way. So essentially D of sigma of alpha is given by e power of sigma alpha divided power of 2 divided by 2 d of alpha. Okay, which is that one is a symmetric way. This is the symmetric way. And we say that let's define the Frobenius linear product for the super operator, and we say that d alpha d beta, essentially, I mean, we can define the A and B, the linear product, and we say that that is trace of A dagger B. And for this one, the result was, if I remember well, it was pi delta of two-dimensional alpha minus beta. So we say that they are complete bases, and then we start to expand any operators in terms of displacement operator. And we say that displacement operator, if you look at the expression for displacement operator of alpha, essentially this is look like e power of alpha A dagger minus alpha star A, which is look like plane wave for us. Okay, So it should look like having the normal Fourier transform, essentially. And we looked at, I think, did we expand the density matrix? I think, yes, we did the density matrix, and we expanded in terms of that. So essentially, the point was that having a density matrix, and we expanded in terms of these complete bases, which essentially we had was d2 of beta divided by pi. And then we had displacement operator of beta. Then we had the trace of rho d dagger of, it doesn't matter, but I'm writing it just to give you the hints to follow, d beta of rho. Okay, so essentially what we have done, we assume that these d operators, they form complete bases. So essentially it's d2 beta of pi, and then we had d beta, d beta. Okay, and then what I have done, I multiply both sides by rho, and when you multiply both sides by rho, then what you will get for the operator of rho, then you will get this explicit expression that I have written here. All right, and then you can translate this. You will get d2 of beta divided by pi, d of beta, and that was, sorry, there is no trace here. Yes, there was a trace, but let's go with a step back. It was d of beta rho, which is what I have written previously, trace of d dagger beta and rho. Excellent. And we discussed about how to expand these, and we got a T operator. All right. And let me write the T operator. I mean, I'm just writing the final form that we got it last time. Essentially, what we got was this, that T operator, which was T of alpha with minus sigma, is given by one integral of d2 of beta divided by pi, e power of alpha beta star minus alpha star beta d minus sigma of beta. Okay. Last time I derived only for one of the sigma, which was the symmetric case. But in any way, you can derive it for any type of orders, let's say symmetric, anti-normal, or normal one. And essentially, the result of this is given in terms of delta function, delta of A dagger minus alpha star, delta of A minus alpha, but in the sigma order. So if that is +1, definitely A dagger will be first, A will be the second one. If it's anti-normal, when it's -1, then the delta, they will switch. So first will be delta of A minus alpha, and then you have delta of A dagger minus alpha star. Okay, pay attention to that. If it's symmetric way, then you have to make a symmetric combination of that. Will be 1 divided by 2 of delta of A dagger minus alpha star, delta of A minus alpha, plus delta of A minus alpha, delta of A dagger minus alpha star. So you have to make it by hand. You have to make it symmetric way. Okay, good. And then what you will get for W, essentially W of sigma, which what we were looking for, finding explicit expression for let's say, quasi-probability distribution is 1 divided by pi trace of rho t minus sigma of alpha. Okay? And let me write down this another time. Then you will get what I mean by this. Integral of d2 alpha, w of minus sigma of alpha, operator of alpha in the sigma order. So these three equations, they are the most important part. This one. And then when you know T, then you know what is going on with W. And then you will get O operator. Is it clear, or should I drive another time for one of them? Anyone having questions how to drive this? Or because previously I drive this for the symmetric case. If you want me to drive it again, just let me know. No? Okay. I will go ahead with the expressions for that. Good. Now I know how to drive T. When I got T, which is simply, if you look at the T, what do you find from the T, guys? Let me ask someone. And by the way, guys, I'm asking you because I want to involve you. I'm not expecting you to know this stuff. We are learning this together. So don't take it personal. So I'm asking you, let's say whom? Mahtab. Can you tell me?
Tell you what do I find in T?
What is this term? Given the fact that I told you, I mean, to all of you that remember, when we do integral on d2 beta, we are doing in the complex plane, right? So d2 beta means that is two integrals together, one on the beta real, one on the beta imaginary. Or you can say that I'm doing on, you know, d beta star. So what you see here, it is not look like a Fourier transform?
Yes.
It just look like a Fourier transform. Yeah. Fourier transform of what? Displacement operator in the normal order of minus sigma. If you remember, I say the displacement operator is look like what?
A plane wave.
What I'm expecting? Delta functions. That's all.
Right.
So the physics is like that. It's extremely simple. Let's guys, if you don't feel comfortable, let's just look at the exponential of alpha beta star minus alpha star beta. Okay, let's do it for yourself as well. Let's do it as a homework. Assuming that alpha is an imaginary, and sorry, it's a complex quantity, and beta also is a complex quantity. Try to find out what is going on with beta I and beta R. Did you get my question? Assuming that now we are looking at alpha beta star minus alpha star beta, okay? Let's do the calculation and find out what is going on with alpha, which essentially alpha it should be replaced by alpha R plus I alpha imaginary, and beta should be replaced by beta R plus I beta imaginary. Okay, let's do that and see what we will get. So I'm doing with you as well. Let's check it all together if what I'm doing is correct. It's alpha r plus I, alpha I. Okay. So essentially, this term is something like that, minus 2I alpha r beta I e power of, I can write it out in this way, it doesn't matter, 2I alpha I beta r. All right, I think you all, have I done properly or is there is any mistake? You have emojis that you can show to me that you are happy or not. Okay. So essentially what I'm doing, I'm taking the 2D Fourier transform of minus sigma oriented displacement operator. And from this, what I will get T minus sigma of alpha. This is what I'm doing essentially. Nothing more than that. Of course, there is a proportional for the coefficient that you have to take care of it. All right. When you know T, which essentially we can find it easily, then we can also find the quasi probability distribution for it. So as soon as we know the T, we know or we find T of sigma alpha, then with the second relation, we can find W. With the second relation, we can find W. So W of alpha, sigma alpha is given by 1 divided by pi trace of rho T of minus sigma alpha. Okay. So from T, I will find what's going on with the W. W also is found. But remember, whatever you have for W, which is plus sigma, what you need is a negative T minus sigma. So it will be the conjugate one. Okay. All right. And also remember that rho in another definition, which also I drive this, is d2 alpha w of alpha with a sigma order t of sigma order of alpha. I think that should be negative. Let me check one of them. I think no, the same value. Okay. All right. Now we will find those specific cases, which is for semi function, we will find Glauber, and we will find Wigner function for specific distribution. Now, okay. All right. Let's start first. Start with t-1 of alpha. So what I'm setting now, I'm looking at sigma, which is equal to -1 for t. What do you expect for these? Look at the previous relation. What was the relation for t to find out? It was pi delta of a dagger minus alpha star delta of a minus alpha with -1 order. What does it what's mean? So delta of a dagger minus alpha star delta of a minus alpha, that should be in -1 order. That's the result, right? What does it mean, -1 order? Flo, can you tell me? It will be?
Anti-normal order?
It will be anti-normal order. So it will be pi delta of a minus alpha delta of a dagger minus alpha star. This is exactly the meaning of anti-normal order. So what is this state? Prove to me next time that is nothing more than alpha, which you can see it also from the nature that you have it. Anyone can make a guess how to calculate this? This is the T operator, right? This is T-1 operator of alpha. And I wrote to you that this is identical to that.
You can plug this in with the Wigner function, probably.
I have not yet found the Wigner functions. I mean, by the way, from here I cannot find Wigner function because Wigner is for 0 case, is not for -1 or +1.
Mm-hmm.
Okay, so the strategy is first define what is T, and then from T you will find out the quasi-probability distribution. How can I express these in this way? Simply.
Using the completeness of coherent state.
Who is that? Who is this person speaking? Yes, Wadi, excellent. Yes, put 1 here, right, and expand it. It is integral of d, let's say beta, all right? divided by pi. I have another pi here, and then I have a delta of A minus alpha. This is beta. This is beta. Delta of A dagger minus alpha star. What is the result of this? Beta will be replaced by alpha. What about the result of this one? Also, beta will be replaced by alpha. That's all. And pi goes away. And the outcome of delta, you know very well, that if you take the integral of a delta function of a function, then everything should be replaced by the value where the delta is undetermined. Clear? Good. Excellent. Now let's go to what Felix mentioned. Here we found t minus 1. I'm sorry, guys, it's a little bit boring, but it's the standard procedure. I don't want to go through what is presented in your book, just putting at the front of yourself and just working with those functions. So we have t minus 1, which now is alpha times alpha. From t minus 1, what can I build up? Look at the t. If I have t here, from the t I can find w, right? So let's do that. So t or w of plus 1 is given 1 divided by pi of trace of rho times the t minus 1 of alpha. True? Good. Which is 1 divided by pi trace of rho alpha alpha. So essentially, it seems to us that Husimi function of alpha is nothing more than 1 divided by pi trace of rho alpha alpha. Assuming that rho is a pure state, which means that rho is given by psi times psi, then that will be simplified for a pure state, that is given by 1 divided by pi of psi alpha square modulus. Now I can understand a little bit better. So if I have wave function, okay, let's talk about pure state because it always is good to understand this equation with the pure state better. And then it will be ensemble for the rest. So assuming that you are giving me a wave function, let's say Kale will give me a wave function of psi. And he's asking me, Ibrahim, can you find the Husimi function, Husimi distribution of that? What I have to do? I have to project it on a coherent state and doing the square modulus easily. So Husimi function or Husimi probability is very natural or expected, that the expected calculation that you want to do. Or should I say the most trivial? Yeah, trivial probability. What I have to do, take the wave function, project it on alpha, doing the square modulus with a coefficient or normalization of 1 divided by pi. Then this is the Husimi function. All right, good.
So the Husimi function is always an actual parallel distribution, not a quasi-parallel distribution.
Yes, we call all of them quasi-probability. You will see it in where. Oh, Eric, I found you. You will see it in a few minutes. What I mean. We call all of them quasi-probability because essentially, should I jump? Yes, because sometimes they will be negative, or sometimes you cannot find them easily. You cannot find them, and that's a problem. Okay. Okay, so now it's clear. Normal order for the probability is Hosimi function and simply projecting the state onto alpha. Or if you work with the density matrix, you have to look at the trace of rho alpha alpha. All right? Clear? Good. What about P representation, P alpha? Anyone can make a guess, will receive 1 mark. But from these, what I have written just here, and you can see it on the screen, how can I find P alpha? So far, what you know, guys, you only know T minus 1. From T minus 1, you built up W plus 1, which is Hosimi function. How can you find out W minus 1 from T minus 1? Manuel?
T plus 1 shouldn't be the same. I mean,
No, it is not the same. It will be, look, T plus 1 will be normal order, which is different scenario. But there is a much quicker way to find it out. I'm asking about W minus 1, which is P alpha. This is my question. No one can make a guess? Look at the first line here. What is written here? Right? So rho, essentially, rho can be expanded in terms of W sigma of alpha, T alpha of alpha. Sorry, T sigma of alpha. Do you agree with me? Let's do it for sigma equal to minus 1. All right. So if you set sigma equal to minus 1, and I know that T minus 1 is given by this, then W minus 1 is look like the density matrix in the basis of what? In the basis of alpha. So if you take the density matrix, expand it in terms of coherent state, the diagonal term will be the quasi-probability of minus 1. Clear? Look, I'm not projecting. I'm not looking at the trace in the basis of alpha. Okay? What I'm looking at the density matrix now. I'm looking only at the density matrix in that specific presentation. Okay, so I will make a line. I think some people are still puzzled how to handle this, right? Let me do a flashback to the previous lecture. Do you remember that we started with rho? I said the rho is a density matrix that you have. And rho can be expanded in any basis that you wish, any basis. And we did it for two specific cases, either photon number, and we do it for the coherent state. Let's do it in the coherent state base. So essentially, rho was given by integral of d2 alpha divided by pi, integral of d2 beta divided by pi. And then what we had two identity here, identity that I added here, another identity that I added here. Oh, sorry, I went a little bit quick. Let's erase this. Yeah. Good. Rho equal to this one. And then that was alpha, alpha, rho, beta, beta. True. And I call these, if you remember, I call these R of alpha star beta with a Gaussian profile, which I don't remember, it was minus, check it out at home, of alpha square plus beta square. We draw this also last time. And essentially, what it will tell us here, if you have a rho and you can expand it in terms of coherent state, the diagonal term will give us the quasi probability of P, which is Glauber. Okay? Questions, or is clear? So that was integral of d2 alpha pi, integral of d2 beta of pi, and then we had this alpha star be e power of minus 1/2 of alpha square plus beta square. Then we had alpha beta. Okay, so this is the entire term. What we have to look for in order to find what's going on with with P alpha, we have to only look at the R of alpha star and alpha. That's all. This is the term that you are looking for. Good. So that's a global representation. And we will see it for a few examples just to clarify. And for W also is the same scenario. For the zero, then you have to make it symmetric way and then applying the condition there. Let's look at a few examples just to have a clear picture how to do the calculation. But in order to have a better picture, it is good to understand the relation between all of these quasi-probability distribution. So you can also look at the Wigner's representation or Wigner's function just in terms of classical probability distribution. You can build up also from the classical probability distribution what's going on with the explicit expression for Wigner representation. Okay, so let's look at the relation between W. We found P, we found Q, and always there is a relation between P, Q, and W that you can find each of them from the other form, because sometimes it's extremely easy to find one of those explicit relations, and then you can find the Wigner representation or you can find the P representation. For example, the relation between W of alpha, which is W0 or Wigner's one, is given by 2 divided by pi integral of d2 of beta e power of minus 2 beta minus alpha power of 2 times p of beta. Okay. Q of alpha is 2 divided by pi integral of d2 beta e power of minus 2 beta minus alpha power of 2 times w beta. And also there is a relation between Q of alpha 1 divided by pi integral of d2 beta e power of minus beta minus alpha power of 2 of p beta. So these are the relation between the quasi probabilities. All right. Let's find the quasi probability for specific distribution, specific states, specific, let's say, light distribution. The easy one, coherent
state?
Yes, exactly, coherent state. So for coherent state, what is the density matrix? Density operator for given coherent state of alpha? 0. It is given by alpha 0. True. How can we find Q? We have to look at the 1 divided by pi trace of rho alpha alpha, which is essentially 1 divided by pi of alpha 0 alpha power of 2. All right. What's that? The two coherent states, they are not orthogonal to each other. They will be given by a Gaussian probability, so which is e power of minus alpha 0 power of 2. Good. So if I have these quadrature, or let's say alpha real part of alpha and imaginary part of alpha, okay, which is the space that I have to plot it, or alpha and alpha star if you wish, then this probability distribution is look like a Gaussian around where alpha 0, right? So if you look at the distance, for example, if that is alpha 0, then that is the probability distribution that you have it. And the area that you do have it, which is look like the uncertainty principle that you do have, that is given by, you have to do the calculation and here finding out what is going on with if I look at alpha is A, that one is look like A, and that is look like A dagger. So, or it's better to look at the quadrature, which is much easier, I would say. So you can look at the x1 and x2, which already we defined that in the previous lecture. So it is look like alpha and alpha star, essentially. It's nothing more than that. One of them is alpha plus alpha star divided by 2, and the other one is alpha minus alpha star divided by 2i. So it's very similar to what we discussed previously. So that will be the delta x2, and that one will be delta x1. And for the coherent state is essentially that's given by 1 divided by 2. okay, for both cases. So what is about P alpha? How can we find P alpha? I will give you a hint. Do you remember that was the relation for P alpha, right? Density matrix should be expanded in terms of these. So rho is integral of d2 alpha, P alpha, which is W minus 1, alpha alpha. What is rho? It is alpha 0, alpha 0. So can I ask someone, anyone wants to be volunteer to answer to this question? What it should be the probability of P alpha such a way that if I place it here, I will get alpha 0, alpha 0.
Shouldn't it be a delta function, delta alpha minus alpha 0?
Exactly. But remember, this delta is 2-dimensional. So P alpha is delta of alpha minus alpha 0 is 2-dimensional, remember. So essentially, look, the phase space is the same. Here, what we plot is Q of alpha. Here, what I'm going to plot, I'm going to plot x1 and x2. I'm looking at a P distribution, which is Glauber's one. And then that will be a point here in the space. Alpha 0. Good. Now, can someone tell me what is going on with W of alpha?
If you introduce it in the first integral, the
Yes.
one you will get just the exponential.
Exactly. Exactly. If you replace it in the first integral, what I will get 2 divided by pi integral of d2 beta e power of minus 2 beta minus alpha power of 2 times p beta, which is delta of alpha minus alpha 0, or essentially, if I want to call it, I will call it p beta is beta minus. All right. Then essentially that will be 2 divided by pi e power of minus 2 alpha 0 or alpha minus alpha 0 power of 2. So again, this is Gaussian, but what's going on with this Gaussian? That is W of alpha, x1, x2. So Manuel, do you want to be volunteer and tell me if this Gaussian compared to Q is broader or is compact?
I'm moving the chat.
Pardon?
I'm moving the chat. Give me a minute. Shouldn't is 0. Shouldn't be like narrower.
Narrower.
No, brother. Sorry,
Broader or narrower?
brother.
Anyone else? Comment from anyone?
Narrower?
Narrower. Because the coefficient is, look, this is look like 2 pi 1 divided by e power of alpha minus alpha 0, right? power of 2. True? Manuel, are you there? I cannot see. Oh, yes, I do see you. So what is happening? Around alpha equal to alpha 0, you have the maximum value, which is 1 divided by e power of 0, which is 1. What is happening when alpha is far away from alpha 0? Then exponential will be increasing. 1 divided by exponential will be decreasing. There is a coefficient of 2 which makes it decay much faster with respect to the previous case. So essentially what I am expecting, that should be a small region. Essentially, if you look at the uncertainty here, I mean, in that sort of formalism, not really the uncertainty, the width that you have it is 1 divided by square root of 2. 1 divided by square root of 2. By the way, I have to be careful with uncertainty. Here, I mean width, which is 1 and 1. Okay? Because I'm talking only about the width of this Gaussian profile, which is happening there. The Gaussian will be like this. Clear, guys? Look, are these 3 different? No, they represent one single quantum state, which is coherent state of alpha 0. But you see it from the mathematical picture, they are very different. This is the meaning of probability distribution that you have it. Okay? Questions? No? Let's do it for something else. The other state, guys?
I have a question, by the way.
Yes, go ahead.
What's different between them, and what kind of information we can get from? I mean, I suppose we can get different information from one of these approaches, I suppose.
Yes, the one, I mean, you know, in terms of understanding the physics, I would say that go with Q alpha. Okay, is a natural projection on coherent state, and that's good. It will tell you what's going on there. While the other one will tell you, if you look at P in this representation that you see, P will tell you that, okay, fine, I'm looking at the density probability, okay? And I'm looking only at the diagonal term, which can be expanded in terms of coherent state. If I look at the Wigner one, Wigner is exactly look like classical probability. Okay, so Wigner can be calculated in any cases, and will give you this the answer that you are looking for. Because at the end of the day, what we want to do with these quasi probabilities, we want to do the average of an operator. So we want to have an operator. You are telling me, hey, Ibrahim, I'm interested to understand what's going on with my detectors when they will click, right? So what is the action of your detector? We'll look at the photon number, right? They look at the photon number of n, right? When they look at the photon number of n, then I'm interested to understand what is going on with the probability that I want to measure. Then I have to look at the average, which is given by this explicit expression, this one, right? Then you know that n operator can be easily written in terms of symmetric way, because n is a dagger a. Then I can write it in terms of a dagger a plus a dagger divided by 2, right? Then Wigner representation, I can easily find it out, which is what I'm doing. Then substitute it here, then you will get the average of the operator O, which is your detector's click. So essentially, at the end of the day, is that, but nothing is more complicated than this. For some cases, as I said, it is easy to find the value. For some other cases, no, it is not easy. You cannot do the calculation. You will see it here in a few seconds. So what is the other state that we can look for the probability or quasi-probability distribution?
Like squeeze state?
Aha, it's your homework. It's gone in your book, by the way. That's the reason that I'm not repeating. Fock state? Let's do it for Fock state. Fock state is n, right? That is the density. All right. So look at the quasi probability of this, Q of alpha, which is 1 divided by pi trace of rho alpha alpha, which is, what is the value? Power of 2. Then if I look at the value, it will be 1 divided by pi. N times alpha was 1 divided by n factorial, if I'm right, because it's power of 2, 1 divided by n factorial, e power of minus alpha square. Then there should be something like alpha square power of n, right? Yes. True. So this is the Q representation for n operator, n state, I mean Fock state. Then what I will expect to see. Look, this is probability based on alpha, right? True. So alpha is changing from 0 to infinity. If you look at the absolute value, there is absolute value appearing in our calculation. So since the absolute value appearing, it seems that it's symmetric. True. Good. Because absolute value alpha can be replaced by alpha real power of 2 plus alpha imaginary power of 2. So it's symmetric. Good. So with increasing alpha, this term will increase. This term will decrease. Is Gaussian beating any polynomial or not? This is one way that always we want to make a wave function to be normalized. We multiply it by exponential of minus x squared, and we guarantee that the wave function is normalized. So Gaussian beats any polynomial. Okay, so what I'm expecting that will be going to 0 at infinity, right? At infinity, somewhere will be 0. Then one of the function increasing, one of the function decreasing. So it has an optimal point. So essentially, the entire of these things will be a ring here. By the way, how many people are working with orbital angular momentum in this community? How many people? No one, essentially. No one. Kate? No. Flo? She's working with OM. Whom else? Flix. Manuel, of course, he's working with OM. No. Josh? No, not yet. Interesting. This is exactly look like the amplitude of Laguerre-Gaussian modes with p equal to 0. So I was expecting that you say, yes, Ibrahim, this is just only a ring and nothing more than that, okay? And remember that the probability also will decrease by number of n. So it will reduce by 1 divided by n factorial. So which is, it's important that you have to look at that quantity.
It's
All
not
right.
a ring.
Pardon?
It's not always a ring. When n is equal to 0, you have just a Gaussian.
Yes, of course. We assume that we didn't deal with vacuum, because vacuum already we discussed about that. So it's a different scenario. So yeah, thank you, Manuel. So is n greater than 0? Okay, so just to be clear that we are working with photon number 1 and up higher. So this is what happens. So that will be the place that you have the probability. And that is Q. Look at P. Right? We have to look at P. Find out what's going on with P. How do we calculate P? As an exercise, P does not exist. Okay, I think one of you asked this question. And how do you check this? If you remember, I gave you the characteristic function, right? At the beginning, I mean, at the beginning of probability, I told you that people, they love to work with the characteristic function. Why they prefer to work with characteristic function? Whenever you deal with polynomials, then you have to go with characteristic function. And here also is the same scenario. You have polynomials in the calculation, and when you look at the Fourier transform of that, then it gives you the derivatives of delta function, and derivatives of delta function in some specific cases does not exist. So P, we'll forget that the P representation for Fock state. What about Wigner one? If we do a little bit of mathematics, P will be given by 2 minus 1 power of n divided by pi e power of minus 2 alpha square Laguerre polynomial of n of 4 alpha square. Okay. Let's plot this. Okay, this is the quadrature. For example, you can set n equal to be 1, okay? Simple case, or 2 or 3 is up to you. What is happening? There is only one difference. So let's go for n equal to 1. What is happening? You have a central part, then you do have a ring around it. This is for n equal to 1. You can plot these. Essentially what I'm doing, I'm plotting just only these. At the center is interesting, is negative. And at the periphery is positive. Okay. So now the question is that, and by the way, this is W of alpha. Now the question is that how the probability can be negative. We are talking about probability, right? This is the quantum nature. And this is one of the reasons that we call it quasi-probability. We don't call it probability. Because in some cases, when the quantumness appears, they will be negative. Okay? So this is something that you should take a note and also remember. Can you plot n equal to 2? Or make a guess what's going on with n equal to 2? You are allowed to look for Laguerre polynomial. Felix, what do you expect?
So we'll have a positive, like a sharp positive peak at 0, I think, and then the negative section will follow like with the negative linear section of the Laguerre polynomial. And then you'll have a positive
Exactly.
bit again on the outside.
Yeah. So you have 3 regions, right? You have 3 rings, essentially. The central one will be positive. The central ring will be negative. And the outer one will be positive again. Okay. All right. This is what we have as the probability and the Wigner representation. I will encourage you guys to look at your book now that you know all of these calculations and you know the source, that how we drive these, we found all of these probabilities. Then you can look at your book and you can find out a few examples. For example, I did not solve 2 examples, which they are very trivial. One of them is taking a lot of time. I think a gentleman asked the question about the squeeze state. So squeeze state takes a little bit of time. Look at the calculation. And the second one, which is easier, is thermal light. You can look at the case of thermal light and try to drive and find out what is the quasi probabilities, all of them, for these 2 cases. Good. Excellent. I will pause this, and then we can go for a short break and come back in about 10 minutes. Is the only problem that we have with Wigner is that sometimes it's negative. And this is not what we know from classical probability theory. Good?
Thanks.
Okay, fantastic. So now we will go to a different world. Now that we know about the photon numbers, we know about the distribution, we know about the coherent states, thermal light, and etc. Now is a step to go forward and talk about maybe optical elements, or maybe talking about let's say different degrees of freedom. It's up to you. Since not all of you work with different degrees of freedom, I will not talk about different degrees of freedom. Maybe polarization will be the only things that I will care about for the time being. Good. Since Henry, you raised a question about number states, let me ask you a question. So we had vacuum, right? And from vacuum, Josh and I, we do the same mistake usually. Josh is WC or W.
Both.
Okay, so we have vacuum, and from vacuum we are building up a photon number, right? So, for example, if I want to go to photon number one, what I have to do, I have to apply
Creation operator.
lovely creation operator. So I will go and I will have 1 photon. Now the question is that, Henry, can you tell me what is the polarization of this photon?
It's undefined.
It's undefined. I have not defined. If I want to define it, what I have to do?
We need a phase operator.
No. I have to just label it. I have to just label the creation operator with the state that we want. Do you remember that we call, essentially we had A of sigma,
yeah,
and K, and we say that
yeah,
these are all modes that we were dealing with. And for simplicity, we took away K. We say that we don't care about K, we don't care about sigma for the time being, but now I care because I'm creating them. So essentially good. So then I have a dagger pi acting on vacuum. Then what it creates for me?
It's one photon in that polarization.
Lovely. It creates this photon in this polarization. For example, if I write a dagger H acting on 0, it means that I have created one photon with a polarization of H. I don't want to talk about serious fundamental questions if whether polarization of H is permitted for a single photon or not. Accept this, okay? Because essentially we talk only about helicity of photon, which is plus and minus 1, and then we talk as one of your a question for your exam. I also asked you to look for the spin angular momentum operator. Okay, fine, good. I want to create 2 photons in that specific mode. What I have to do? Anyone else wants to volunteer and tell me? I want to have 2 photons to be created in same mode.
You apply the square of the creation operator over square root 2?
Exactly. Do I do a square root of 2 acting on vacuum? Then what I have 2 photons, which all of them, both of them, they have identical polarization of H. What about N photon? I think, Eric, you mentioned, so you can go ahead and just tell me.
A dagger n over a dagger to the n over square root of n factorial.
Lovely. So then I have N photons in the polarization of H. Beautiful. Good. I did not talk about K vectors, but I assume that all of them, they have the same K vectors. They are propagating, right? Good. Or having the same frequency, which is what we were caring about them. So this is something that you should remember and you should keep in your mind. Then when you deal with modes, you have to label your creation and annihilation operator with those specific modes. It's important. Else, you will be getting confused easily. Okay? So remember, essentially A, sigma, and K. So they are labeled by sigma and K. By the way, some people like me, and maybe members of my team, sometimes we prefer to label them with spatial mode. So we label A with polarization, with radial mode, orbital angular momentum. So this means that acting on vacuum, I have 1 photon in polarization of pi and spatial mode of P and L. Okay, I don't want to talk about these. I just want to tell you that expect these. If you see in textbooks or if you see some articles, this is what is happening. And by the way, these spatial modes, essentially, what I label them, it is nothing more than this K vector, but in a different representation. Okay, if you look at the K vector, essentially you have omega, you have Kx and Ky, right? I fix Kz by omega because the sum will be equal to omega divided by C should be equal to K square, K. So then Kx square, Ky square plus Kz square is equal to omega square divided by C square, okay? So it's fixed. So nothing is more than that. All right, now I'm dealing with many photons. I'm dealing with n number of photons, so m number of photons. And now I want to understand what is the action of optical devices there, right? So remember, this is the general story. And now on, since I want to build up optical setups and I want to tell you what's going on with, for example, Humphrey-Brownman trees, I want to tell you what's going on with, for example, GN function, what's going on with detectors and etc. I want you to understand what's the action of each of those devices on photon numbers. Good. What is the simplest things that you can get it in laboratory? Manuel. You worked in the laboratory, right? Your microphone is mute. So Beamsplitter is the first thing, or something else.
Water wave plates.
Oh, that's polarization. So we don't want to work on the specific degrees of freedom.
Mirrors.
Lovely. What is the action of mirror, guys?
It'll change the orientation of the K vector.
Yes, it flips the orientation or the direction of the K vector. How many people agree with me? Okay, 2. Whom else? Flo, 3. Kevin is shaking. Heads, Kate as well. Mahtab as well. So I see. Okay, good. Caesarea, lovely. So we all agree that the action of a mirror will be changing one or all components of the K vector. So we have to drive this. I mean, just see in our coordinate what is happening. So assuming that is, oh, funny color. This is the propagation direction of K. Why say one or all? Because it depends on the orientation of the mirror. This is K vector coming in. You have a mirror which is oriented in this way. What it does, it just sends it back. So K essentially will be inverted to minus K. This is the action of this.
It's perpendicular, am I right?
Pardon? It's completely orthogonal, yes. It's completely orthogonal, that sends back. What is happening if I rotate the mirror by alpha? So this is this other scenario that I have. So it comes here. Then the mirror is, let's look at the orientation. I plot it like this way, okay? So the angle between these is alpha. The beam will be reflected in this way, right? And minus alpha here. So only one component of the K vector will be flipped, right?
Yes.
It will not act on X and Z, it will only flip Y direction. So remember that the action of mirror will be one of those things. So it can be very complicated depending on the orientation of the mirror, but you can understand it. So don't forget, do not forget the action of the mirror, okay? So mirror will change the photon direction. Or essentially K will be acted, will be changed. So M acting on A of K, then it will be A of M acting on K, okay? So that will be rotated or will be switched, that you have to properly sign this. For example, in Mach Zehnder, it is extremely easy to understand because it's going in only two in a plane. So you understand what's going on. Is going up, then it will go to the left side, or if it's going down, left side, it goes up. That's all. Okay. So you have to remember this. I'm just briefly mentioning this. When it comes to act, we will look at them. We will find the explicit expression for them. And remember also that mirror, what it does, that is true that it changes the direction, but also it does some strange things, like
Adding phase.
adding a phase. Remember that for one of the polarization adds a phase. Okay, so this is something that you should remember. As a homework for yourself, go and look at the optics book and find out the action of mirrors properly. Even mirror or combination of mirrors will change the polarization of light. You can go with linear polarization. With 4 mirrors, you can end up with a circular polarization. Okay, because you can control the relative phase between what we call it S polarization and P polarization that comes in. So those things you have to keep in your mind. They will not tell you in textbooks. When it comes to building up setups, you will get problems. Good. I will not talk about these so far. Later on, we will discuss about them. But remember that mirror by itself is very complicated. If you go to website of my group, go to, I'm sure that you can check it out. There is a section which is written software. Okay. If you go to the software section, there are 2 things there. One is a LabVIEW code. The other one is a quantum optics mathematical package, which is written for Wolfram Alpha. And there, all of those optical elements like mirror, like Dover prism, like beam splitters, like quarter wave plates, or whatever, holograms, all of them, they are defined properly. Yeah. So you can, even if you have problems, you can go there and check out if whether you understand properly or not. For example, we have different type of mirrors. They can be silver coated, or they can be dielectric mirrors. The action of these 2, they will be different. Good. So, Manuel, I'm not expecting mirror to change the distribution of photons, right? It changes only the K vector. Nothing else will be changed, unless the mirror is absorbing, which is different scenario. But we assume that all of the optics that we have, they are non-absorbing material. So they are unitary action. You mentioned the other optical element that you work in the laboratory, which was?
The beam splitters.
Beam splitter. This is extremely important. Beam splitter. Good. How many people did not work with beam splitters? Or how many people they worked with beam splitters? You worked. Okay, Cecilia, good. Arman as well. Reza, of course, I'm sure. Kyle? Or Kale? Sorry. Yeah, you worked. Who did not? Kate, of course you worked with. Yeah, Mahtab? No, you did not work with beam splitter. Okay. So what it does, beam splitter, it has 2 actions. Remember that. So usually we show beam splitters with a cube like this. Is our beam splitter. It has 2 inputs and 2 outputs. Okay. Or I could say that why I'm going this way. It can have 2 inputs and 2 outputs. It's up to you. How do you orient it? Good. Let's go with the black one because it's easier, just for simplicity. Can I have a beam splitter which has 1 input and 2 outputs? Can I have it? Kevin says yes. Who says? Whom else? Do you know what I mean? Can I have a beam splitter which 1 goes in and 2 goes out?
Classically, yes.
Now, it doesn't matter, classical or quantum, doesn't matter. 1 in, 2 out.
Do you just mean like one input beam?
Yes. No, I'm saying that can I have a beam splitter which doesn't have one port? It doesn't have 2 ports, has only one port. Of course, I can feed it only once here, right? And then it will be transmitted or reflected, right? I know that, it's not a big deal. But essentially, it has one port which is empty.
What about like a knife edge? What is this looking like?
No, you are dealing with special modes. You're picking up those 2 regions. No, you cannot have it. As a homework, do it at home. Try, look for unitary action. I'm giving a hint, which you have 1 input and you will get, or you end up with 2 outputs. It is impossible. Okay, good. Those small things are details, by the way, but they are really beautiful mathematics hidden there. Good, so I have a beam splitter. What is the action of a beam splitter? You go with 1 beam, or it has 2 inputs, and links these 2 inputs to the 2 outputs. All right. So, Mahtab, did you get the point? It looks like a half mirror, essentially. It looks like a half mirror, very, very thin half mirror, which if you watch it, you can see a little bit of residual from back. So it works like half reflected. Okay. So now let's, for simplicity, I will show it with this. Okay. With only 1 line. And I will say that this beam splitter. Kevin still is thinking about 1 to 2 ports.
No, my neighbor just let their puppy outside, so I'm kind of
Oh, okay.
slightly distracting.
Okay, so this beam splitter has 2 inputs, which I call them A and B, and 2 outputs, which is C and D. Books, they call it with different ways. So they call it A1, A2, D1, B1, B2 also. It's up to you. But what is important that you do have 2 inputs and 2 outputs. All right. So classically, this beam splitter has a reflectivity and transmittivity. True? And I believe that this beam splitter also is unitary. So I mean that it does not absorb light. So the power should be 1. So the power of the output should be equal to power of input. Let's look at the field. So I have a field which classically goes in, which is EA. I have a field which classically goes in is EB. At the end, what I have, I have ED and EC. How ED and EC, they are linked to EA and EB. EA goes in, a portion of it will be transmitted, which is, I call it is TEA, and a portion will be reflected, which is REA. True? What's happening for the other one? EB goes in, then a portion will be transmitted EB, a portion will be reflected, which is reflected EB. Since the system is linear, I'm expecting that the field, by the way, this is field, the field will be at EC superposition of TEA plus REB. So I mean that this will be summed out with this one, summed up with this one, and ED will be equal to the other one, which is REA plus TEB. Do you agree? All right. So essentially, EC and ED will be equal to T R T of EA EB. Do you agree?
Is it all right that this matrix is not unitary?
Pardon?
Is it all right that the matrix there is not unitary?
Why it should not be unitary?
But this one isn't, because the columns aren't orthogonal.
This should be unitary. We
Maybe
are,
there's a minus sign somewhere?
no, we will work on that.
Okay.
R and T, they are complex quantities.
Okay.
Okay. So this should be unitary, right? This is the action of Beamsplitter. Do you agree, guys? This is the action of Beamsplitter. Essentially, this is what links input to output. So Beamsplitter acting on input, let's call it the state, will give me output state. All right? Fantastic. And we agree that the action of Beamsplitter is unitary. What does it mean? Should I say this? Eric, do you agree with that? Eric?
Yeah.
Excellent. So let's work on this and find out the relation between T and R such a way. By the way, remember that T and R, they are Fresnel coefficient, by the way, right? Fresnel coefficient for transmission and reflections. So they are complex quantity, essentially. So they are element of C. They have a phase and they have an amplitude. Good. Let's do that. So it will be T R T times the rest is the conjugate, which will be, and transpose conjugate, which will be T star R star. Okay. T R star and T star equal to 1 1 0 0. Good. Then from this, what I will get, the T square plus R square should be equal to 1. And from the second term, I will get T R star plus R T star should be equal to 0. And the other two is a degenerate situation, so is identical to what we get. So I look at only at these two terms, this one and that one. The other two will be identical. So one of them will be conjugate, essentially. Good. So what I will get, if T has a T magnitude, e power of I phase of T, and R has R e power of I phase of R. I will replace it here and I will try to find out the relation between phi T and phi R. Good? Are you following? So I'm trying to understand what's going on here. So the first equation is fine. It tells me that it's really unitary. So it's just the power is conserved. Nothing else will happen. The second term will tell me that T times R, and then TR star will be e power of I phi t minus phi r multiplied by plus e power of minus phi t minus phi r. That should be equal to 0. Okay. I just multiplied them together and I took away the TR, which that tells me that T and R, they cannot be, the magnitude cannot be 0, because that's a condition that we do have it for Beamsplitter. Then essentially we deal with cosine of phi t minus phi r to be equal to 0. So it means that phi t minus phi r is odd values of pi divided by 2. So it can be pi divided by 2, 3 pi divided by 2, 5 pi divided by 2, and etc. We care only about the first value, so which is this. Good. So then I will write it down. Beamsplitter action essentially is given by, let's take away e power of I phi what should I take out? Phi t. Okay, because we had the phi t. So that should be t. That should be r e power of I phi r minus phi t, r e power of I phi r minus phi t, and that is t. Do you agree? Which is e power of I phi t, t r e power of I pi divided by 2, r e power of I pi divided by 2, and t, then that is e power of I phi t, t, I r t. Good. Any questions so far? Or is clear? Clear? Doesn't matter. Is it phi t minus phi r or inverse is the same, because it's a cosine of this equal to 0. So if you're happy, you can go with this way just to make yourself happy. Doesn't matter. Because it's a cosine. Cosine is a even function. Okay. Without loss of generality, I assume that the global phase of e power of I phi t, that is equal to 1. So essentially phi t, I will set it to be equal to 0. I care only about relative phase. So you know very well that in just few cases, the global phase is important in optics. And in other cases, you can just neglect the global phase. So action of Beamsplitter essentially is given by T, IR, IR, T. Is that unitary, Eric?
Yeah.
Okay, now we are happy all. Good, all right. So,
Now,
yes.
and here we assume that R and T are real.
Yes, we assume that now hereafter, I replace, I neglected the absolute value of T and absolute value of R, and simply I replace all of them with T and R, because I assume that the phase is considered, right? Just I don't want to handle absolute value all around all of them. Okay. And T here is absolute value of T, and R is absolute value of R. So it's just the magnitude. Good. So, and I know from this equation that ECED was related to EB. So ECED was given by Beamsplitter action on EB. And AB was ABCD. Okay, good. All right. So now we found the action. In quantum optics, always is good to look backwards. So you have to look how the outcome and the input, they are related to the output, because we know what is the input mode, right? So we know what is going on with input operators. And then if we know how the input operators are linked to the output, everything will be simplified. But here in this expression, input is related to the output. So output is expressed in terms of input. So what we have to do, we have to look at the inverse of these. So EA, EB, look at the BS inverse acting on EC, ED. Clear? Now what I'm doing, input, if you have input, do the beam splitter, and then you will get output. Here I'm doing completely opposite way. I want to know how output is linked to the input with the beam splitter, because that's a unitary action. Right? If you remember again, the field that we deal with, we say that if you have a classical field, how do we do the quantization? We have a creation operator and annihilation operator with positive and negative frequency. Essentially, we have an E plus and we have an E minus. Of course, you have to go with e power of I k dot r, and that was e power of minus I k dot r. And between them, there was a minus sign, that was a summation, you know, all of the things that you know very well, even better than me. So that was the action. And for the time being, we neglect polarization, by the way. We don't consider the polarization. We assume that polarization is identical for all of them. Good. So the field can be replaced by creation operator, by annihilation operator with a positive sign, while for creation operator, it should be assigned with a negative sign, right? Clear? So whatever I derived here can be replaced by annihilation operator because it's directly proportional to the field, right? So essentially, annihilation operator of output C and D with the beam splitter inverse action is linked to annihilation operator of A and annihilation operator of B. Good? What I'm doing, I'm just doing the quantization by hand. The electric field that I have it, I just look at the annihilation side of it, not the creation side. Creation side always is the conjugate, which is easy, can be done. Let's do that. Okay. So then beam splitter action was T, R, I, R. What is the inverse of this? Can someone do the calculation?
The conjugate transpose.
It will be T.
The same thing with minus I.
Exactly. We already did the mathematics for this. So annihilation operator of A and B, they are linked to T minus IR T acting on C and D. So let's look at the physics. Physics is like that. If you have a beam splitter, if you go with mode of A and mode of B, then at the output, what we have a mode of C and mode of D. Okay, the annihilation operators between them are related to each other by this relation. Can you find now A? A simply is given by TC minus I R D hat. And B is given by minus I R C hat plus T D hat. Are the two modes of A and B different? Yes, of course they are different. They are two sides of the beam splitter, right? And associated to this, we have also creation operator of B dagger, A dagger, C dagger, and D dagger. Remember, I'm not looking at the photon numbers. They are different, so I'm writing this way. Okay. How can we find the dagger operators or creation operators? I have to take the dagger of these expressions. So A dagger will be T, which is real now, C dagger minus I, oh sorry, plus I R D dagger. And B dagger is given by plus I R C dagger plus T D dagger. Clear? Good. Sorry, Henry. I'm sorry, it's boring.
The coffee's run out.
Yeah, go for coffee. I just had it in the break. Good. We are almost there. We are almost there, and I think it is important to learn these bases very clearly. Good. Now we know annihilation creation operator. The first thing that someone may ask, by the way, where is Kevin? Kevin. Okay. So you say, sorry, I see just one side of the screen, so I don't see all people. You say that there is a device which can take one port, has one port, and giving you two outputs.
Possible outputs, yeah.
Yeah, essentially the other port is vacuum. It should be 2 by 2. It's impossible without 2 by 2. That's the lying down in terms of being a unitary action or Hermitian, essentially, that you can look and find out. But in classical world, what we do have is just a simple beam splitter, which one port is feeded, the rest is not feeded, and then the action will be just splitting out. But in the quantum world, the other side is fitted with vacuum, which vacuum introduces noise to the system. Okay, let's see what I'm going to do. I mean, in terms of, let's say, very simple scenario. what is the simplest scenario manual that you work also in the laboratory? How many photons should I send to the beam splitter? I cannot hear you. One photon. Which port? Up to you. Tell me. A?
Yeah.
Okay, let's say. So manual says to me that, Ibrahim, since I know this is the action of beam splitter, let's now work on the and find out what will be its action on one single photon. What does it mean that I have one photon here going in? What is the polarization? I don't care. Is whatever it is fixed. Okay. It's going to the port of A, and what is going to the port of B, Manuel? Vacuum. I hear, yeah, I could read vacuum on the port of B. So essentially, input state that you have is 1 in the port of A and 0 in the port of B. Do you agree with me, guys? This is the input state. True? Who told me? Yes, it was Henry. He told me that how can I build up photon in terms of photon numbers? How can I build up photon numbers in terms of creation operators? So this is not. This is simply creation operator of A acting on vacuum. Do you agree? By the way, this is the formalism that I think previously I used. It's a tensor product of those vacuum, because vacuum is not only single vacuum, it's many modes. So if you talk about general vacuum, is many modes, zero excitations. Okay. Do you agree with that? Yes.
Create that operator have like a subscript to denote which it actually applies to, though.
So I label it with A, which A assigns to the mode that I have.
Right, yeah.
Yeah. Okay, good. So now I want to understand what is going on with output, right? I want to go understand what's going on with output of C and, let's say, C and D. I have no clue. I mean, you know, but let's do it in a quantum formalism. So let's go and ask someone here, Tenglu. Hey, can you tell me, Tenglu? I want to link the input to the output. So how can I replace a dagger here? You are muted.
Yeah, I was thinking. So
A dagger is here, right?
Yeah.
Okay, let's do that. So let's replace a dagger, which is T transmittivity of the beam splitter, a C dagger, plus I R D dagger, acting on 0 and 0. Can you tell me now the result?
You become so let me see. So you become
1 at mode of C, right?
And then 0.
0 at the mode of D.
Yes, and plus IR.
Exactly.
And 0, 1.
0 at the mode of C and 1 at the mode of D.
Yeah.
Ah, beautiful, right? What I get now, the output, it is correlated. You cannot write it as a simple product of C and D. These two, they are linked to each other, which if I want to write it down, it will be T as 1 photon in C, 0 or vacuum at the mode of D, plus IR, 0 at the mode of C, and 1 at the mode of D.
So
If,
for
yes,
for sort of classical light, the beam splitter would just take input light and have output light, just both have output in the two modes. But here it's a superposition of having light in one and having light in the other.
I will come to your question. What do you mean by classical light?
Exactly. Too many photons to count.
No, tell me. Yes, you are right. I mean, tell me what you mean by classical light. You learn quantum
And
optics. Yes.
just taking the electric field as a granted.
No, look, forget about classical optics. Now you learn quantum optics language. In the quantum optics language, you should be able to deal with classical light as well, right? I can
A coherent
describe the
state.
classical light. What?
Coherent state?
Exactly. We will drive that.
Cool.
We will drive that. Yes. Good point. Okay.
Awesome. Thank you.
Sure. Anyone questions, guys? No? Okay. So it is very interesting that if you deal with a single photon going to a beam splitter, then the photon will be in coherent superposition of the two ports, C and D. You cannot localize it. You cannot say that is in C. You cannot say that is in D. Some people, they call these single photon entangled state, right? Some people, they call that. I don't like it. Personally speaking, I don't like it. In terms of having entanglement, you need to have two, let's say, two particles, essentially. I can talk about this, how people from such a scenario, you can create entanglement, right? So let's ask a question to someone. Who wants to be volunteer without knowing the question? Thomas, you're brave, I'm sure. So, Thomas, if I am looking only at the gate of C, right? I'm only watching at the gate of C. What do I see if I repeat this experiment many times? The first time.
You'll see a single photon.
Which probability?
Probability R squared.
T squared. Because you're looking at
C.
right,
a D.
Yes.
Sorry.
You are looking at this term, right?
Sure.
One photon in C.
C. Yes. I did. That'd be T squared. Yeah.
So with the probability of T squared, you will see the photon, right? Yeah. So essentially, let's go with simple beam splitter scenario, which they call it 50-50 beam splitter. 50-50 beam splitter, which means that R is equal to T is equal to 1 divided by 2. All right? Sorry, 1 divided by square root of 2.
Yeah.
And the first time that I'm repeating this experiment many times. The first time I'm sending in, with a probability of 50%, you will detect the photon in port of C, right?
Yeah.
So means that either you will see it or you will not see it.
Yes.
With equal probability. What is the state of C? Or you don't have any knowledge about the port of D. You only talk about port of C.
It's a mixed state.
Exactly. Since you are only watching at the port of C, you are tracing over port of D, and the outcome will be a mixed state of 1 T squared of 1 C, right?
Yeah.
Plus R squared of 0 C, 0 C. This is important. If an observer looks at the C port only. Excellent. Thank you, Thomas. Beautiful. All right. The coherency essentially is destroyed. And if you remember, I say to you that guys, we can create some sort of entanglement. How can we create entanglement with this scenario? How can we create entanglement with this scenario? So I have only a beam splitter and a single photon that goes in. By the way, I shouldn't go with the circle because photon is not localized. So I go with a single photon here. Then I have an atom which has ground state and excitation state. I have another atom here which has a ground state and excitation state. And energy of the photon will give you exactly the excitation. So I have atom number 1 and atom number 2. If I do the same experiment, then if the photon is reflected, which is what we have it, the state, or will be transmitted, then that will be translated into atomic states. So the atom state either will be in excited one, so T. If one photon is in port of C, then the atom in the port of C will be excited. This is atom state. And then atom in D will be in ground state plus IR. Atom in C will be in ground state. Atom in D will be in excited state. This is the way that people, they can create entanglement from a single photon and a beam splitter, but they need 2 atoms essentially. And the 2 atoms will be entangled in being excited or in being in the ground state. Clear? Remember, in order to have entanglement, you need 2 parties. You need 2 particles. By the way, this is my personal view and perspective. Okay, so this, not all people, they agreed with me on this concept. Good. How many minutes are we? Have 20 minutes. I will be able to finish some exciting stuff here. So let's look at the state, the final state. Final state. Let's write it down. Is T 1 C 0 D plus I R 0 C 1 D. Okay, so this is after the beam splitter. That's the final state after the beam splitter. I know the operators now, right? Let's look at expectation value of N3. Oh, sorry, N3. What do I mean by N3? ND. ND. What I'm doing, guys, anyone can tell me? N is a photon number operator. Essentially is this. Is D dagger D. Valerio, can you tell me what I'm doing?
And you're calculating the expectation value of the integral D.
So physically means I'm looking for number of photons in port of D. What is your expectation? Look at this. Right? Do it as a homework. Right? I'm expecting that will be the result. Look at N of C, which is C dagger C. What I'm expecting as a result?
T squared.
T squared, lovely. And if we look at N D plus average of NC that is equal to 1. So I'm expecting, or in general, if you send n photons, it should be equal to n input 1. So this is the action of being unitary. I have a question. Anyone that can answer will get 1 mark. What is ND NC? Which means that I do have D dagger D, C dagger C, which is essentially, since D and C they will commute, then it will be identical to C dagger C, D dagger D. It's the same.
Would it be 0?
Who said, Eric? Exactly. What does it mean? Eric? Can you hear me? Hello? Can you hear me? Oh. High tech, guys. Sorry.
You know too much, Ibrahim.
I know too much?
Yeah, they're silencing you.
Oh gosh, my apologies, guys. No one can control these sort of things. Oh gosh, let's go and see whether I can enter. Okay, so while we are waiting for this, what does it mean, Eric?
I like what Felix said, that you can't expect to have a photon in both at the same time.
Exactly. The meaning of finding the two sites having photon is 0. So photon will be in one of those two. When it comes to the detection, right? When it comes to the detection things. By the way, something interesting will come. It is recorded, so I can hear, I can see what you say when I was not there. So anyway, yes, that is exactly the meaning. So when you look for when you look for ND and NC, do you expect to have 0 value, because there is only one photon. A photon cannot be in 2 places. It can be in superposition. When you detect them, there is only one photon, not more than that. Okay, we can go with very complicated scenario, but let's go for a question that Eric asked me. All right, I need your help, Eric, by the way, in this specific scenario.
Just 1 second,
Yeah.
everyone. So
Sure.
if you have more than 1 photon, this is not 0 necessarily.
No, it's not 0. It can be 0, but not necessary. Your answer was just perfect, I would say. So Eric asked a question regarding what's going on with classical world, right? If we have a beam splitter, can we get the classical expectation? So I asked him, what do you mean by classical? He said coherent state. Okay, someone help me to write down the A dagger and B dagger, guys. So remember A dagger and B dagger because I need them. Okay, so write it down and tell me. When we say coherent state, we mean that we have a beam splitter and we have a coherent state coming in, which the coherent state is alpha, and this port is 0, right? It's vacuum, essentially. Port of A is vacuum, B is here, and C, oh, sorry. This is A, this is B, this is C, and D. So we have alpha in the mode of A, What about mode of B is 0? True? We are only sending a coherent state there. So can you tell me, Eric, how do you build up a coherent state?
You use the displacement operator on the vacuum.
Exactly. What is displacement operator? E
E to
power
the
of
alpha A dagger minus A.
alpha A. Remember, we are using A and A dagger because we are dealing with the mode of A. We are not dealing with the mode of B. If it was B, we have to write B dagger and B, right? So then it is 0 in the mode of A and 0 in the mode of B. Good? Perfect. So, Eric, can you tell me what was the relation between A and C and D, and A dagger also between C and D?
A is TC minus IR D.
D and
And then
yeah,
A dagger is TC plus IRD.
IRD dagger.
D
True.
dagger, of course, yes. Sorry.
Excellent. Now what I have to do, I have to replace A dagger and A inside of this equation. True?
Mm-hmm.
Let's do that. So then after the beam splitter, then that will be exponential of alpha TC minus IRD minus alpha star TC dagger plus IR D dagger acting on vacuum.
I think you might have swapped the position of the A and the A dagger.
Pardon?
Accidentally. I think you might have accidentally swapped the position of A and A dagger.
Oh, but you mean it should be like that?
I think it should be daggers on the first term and then no daggers on the second term.
Oh, yes, thank you. You are right. Yeah, I got it. So that should be dagger. That should be dagger. Thank you very much, Eric. I think, yes. And this one.
I'm guessing I don't get a mark for this one.
No, you don't get anything. I have to take your mark out. Kidding, of course. Thank you. Then is the vacuum, which is vacuum that we deal with. Now we know that we are not dealing with the vacuum in the mode of C and but sorry, A and B. We are dealing with vacuum in the mode of C and D. Okay. Good. So now let's cast them together in a different form. C, I will keep them together, C and C dagger together, and also D and D dagger together. So it will be E power of alpha. Let's take away the T out. Oh gosh, my bad. Oh, let's write it in a different way, even elegant. Alpha T, C dagger, minus alpha star T C. True. Essentially, I have to write plus the other term, but I know that C and D, they commute. It is easy to prove that. You have to go back to the first equation that I had. You can there prove that C and D, they commute. Dagger or whatever, you can write all of them. But C and C dagger, they will not. Okay, so you can go back and from here, even you don't need to go with the theorem, Baker-Hausdorff-Campbell theorem. Easily you can expand it, so you can get E power of I R alpha D dagger minus I R alpha star D acting on vacuum of 0, vacuum of D. Do you agree? I inserted I inside of the parentheses, which I do the conjugate, okay? And the conjugate will act only on alpha and I, because R is a real quantity. So the first term, acting on vacuum, will give me a coherent state, right? What is the magnitude of coherent state? Is alpha T. In the mode of C. What about second one? Will give me
I alpha R.
I alpha R in the mode of D. Good. Example. When you deal with a 50-50 beam splitter, 50-50 beam splitter, what I will get? I will get T is equal to R equal to 1 divided by square root of 2. Then that becomes alpha divided by square root of 2 in the mode of C times I alpha divided by square root of 2 in the mode of D.
This seems like it automatically gives us the change of phase from reflection.
This will give us the phase, yes, automatically.
Oh, cool.
Yeah. And moreover, what is the electric field? Do you remember what is the relation between electric field and alpha? Alpha square will give you the intensity, right? So if you look at the intensity, you will see that intensity is constant. Essentially, a field will be divided in 1 divided by square root of 2 in each side, right? This is what we expect in classical regime as well. Some people, they call this classical entanglement. I hate this word, by the way. I'm saying in public many times. I hate this word because if you do proper calculation, you will see that essentially the quantum state is a tensor product of mode C and D. There is no superposition of the two. Unfortunately, people, they look at the single photon regime and they say the field is a coherent superposition of these two sides, and they will write it in a wrong way. Okay? So remember, when you do with the classical things, classical light, except you expect to get the same physics. You don't get something very strange. All right. Anything else? Flo asked me about other number photons, right? Flo, before going there, I want to surprise you with something else. I will answer to your question. I will not forget. Let's go with a different one. I have a beam splitter. I have one photon coming in. I have one photon coming in with the same polarization, with same spatial mode. All of them, they are identical, so I don't label the annihilation creation operator except the position, which they are coming from port A or port B. So this is port A, one photon in port A coming in, one photon coming from the port B. And then that is port C, and that is port D, which that's a question that I have for you. Okay, let's do the mathematics. What is the input state? Is one photon in port A and one photon in port B. All right? Can you write in terms of annihilation and creation operator? Because we have to always work with vacuum and transforming the creation and annihilation operator in the proper basis that we want, proper modes, essentially. So, Flo, can you tell me how can I write these 1A, 1B in terms of creation operator?
A dagger, B dagger, acting on 0.
A dagger, B dagger, exactly. acting on vacuum, which is vacuum of 0 and 0. Can you tell me what is, after the beam splitter, A dagger will be transformed to something else, which is in terms of C dagger and D dagger, and B also will be in terms of something like C dagger and D dagger. Can you tell me this? I think I know for A dagger because we just previously used that. So it will be C dagger or D dagger. Can you help me with the other one?
It's IRC dagger plus T D dagger.
C dagger plus D, T D dagger, right?
Yeah.
T dagger. Thank you very much. Acting on vacuum, which is 0 and 0. Remember, these vacuum now they are in output, so they should be C and D. Good. Excellent. So we had 2 photons coming in, and now we are looking at the output. Let's see what we will get. Look at that. So we get, remember that C and D, they will commute with each other. All right? Good. And now we do the calculation. So it will be I, R, T, C, dagger square plus T square C dagger D dagger plus minus R square C dagger D dagger plus I R T D dagger square acting on vacuum 0, vacuum D. Good? Clear? Okay. Sorry, Flo, I'm asking you. You are the only one that I'm asking question. So can you tell me what is the first one acting on the vacuum?
Gives IRT2.
RT2, okay.
And some square root factor of 2, I think.
Yeah, we do get a square root of 2. And that is 2.
2 and then 0 for D.
2C and 0, right?
Mm-hmm.
What about the other one?
T squared 1C 1D.
Okay.
Minus R squared 1C 1D.
C 1D.
And then square root of 2 IRT 0C 1 at 2D.
0C and 2D, right? I feel that this square root of 2 should be in the denominator, guys. Am I right or am I wrong?
No, I think it should be in the numerator.
Okay. We will do the normalization factor later on. Good. Do you agree with that? Okay. So look at each term. What does it mean? This is your beam splitter. Means that the 2 photons will be in C. Right? Perfectly the same. What about the second term? 1 will be in C, 1 will be in D. What about the third term? 1 will be in C, one in will be in D. What about the last term? Both of them, they will be in D. Which is not strange, it's just probability. So if you send one photon with the probability of T and R, they will be either this way, okay? If you send two photons, you have two of those probabilities. It will be end up with four possible situations. Now look at the case that you have 50, yes, there is some problem, 50-50 beam splitter. Look at that case. So it means that T is equal to R is equal to 1 divided by square root of 2. So the first one will be square root of 2, I, that will be 1 divided by 2. Oh, the normalization showed up here, sorry. 2C and 0, D. The other one will be 1 divided by 2 of 1C, 1D, minus 1 divided by 2. Oh, 1C and 1D. Oh gosh, something is wrong here. 1 plus I 1 divided by 2 square root of 2 of 0 and 2D. These two terms, they will cancel out each other. It seems that this term and this term for 50-50 beam splitter, they will cancel out each other. And then I will get I factor 1 divided by square root of 2, 2C and 0D plus 0C and 2D. So previously, I had, if you go with 50-50 probability, by the way, I'm just talking about 50-50 probability. 25% of the time is this possibility. 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 This is the logic that you know from classical mechanics as well. However, if the beam splitter is 50-50%, let's say 50-50, then only the last two, first one and the last one will remain. So essentially, you do have either the two photons will be reflected, transmitted, let's say one reflected, one transmitted, or the other possibility, which they both go to the port D. Okay? And what is the probability of these two? 50%. Interesting. So if I have two photons, which they are identical, by the way, because I say that apart from just only coming from the different port, they have the same quantum property. They are the same mode. Essentially, I will get them to exit from the same port. They call these two photon interference, or Hong-U-Mandel, or oh gosh, I have forgotten her name. Loden. Gosh, why I'm so bad at remembering name. I can help you. No one can help me with this? Okay, I can look at my Hong-U-Mandel. Hong-U-Mandel. We just wrote a review paper on this with members of my team and some international collaborators. Let me just remember all of the names because this is important. It should not be assigned to only single person. It should not be this. Hong-U-Mandel effect. Figure 1, 2, 3. Okay. Okay. So 3 people, essentially, they did this experiment, or they predicted the experiment. So one is Hong, Wu, and Mandel, which they did it in 1987. And the other person is Ferran and Loden. And the other group that also at this, almost in the same time they did that is Rarity and Tapster. Okay. As I said, Frederick Bochard, Alicia Sid, Ingwen, Filippo, Yao, Fabio Sharin, and myself, we wrote a review paper about this effect that was published in 2021, just this year, beginning of this year. It's something about maybe 20 pages with all applications of Hong-Wu-Mandel. This Hong-Wu-Mandel is the key element for quantum computations with photons. It can be used to build up gates and everything else. I mean, doing the Bell state measurement, doing optimal quantum cloning, and many, many other applications. So it is extremely important. If you want to find, I mean, this is the physics and concept. If you want to learn more, just go to our website and you can look at that paper. The title is To Photon Interference, the Hong-Wu-Mandel Effect. But essentially, we have to give the credit to all of these 3 groups that essentially they had. Ferran and Loden, essentially they did, I mean, it was very natural for them how you find the Q representation just by looking at the projection on the coherent state. They look at what is the action of lossless beam splitter. John Rarity and Tapster, they did the experiment, but they had not published it. It was so interesting. They had it only, and at that time, it was not look like right now that everything will be connected by the internet. So when they saw the article in PRL published, then they decided to not publish it. I think maybe later on they published in some minor journals. So anyway, this is at the heart of quantum mechanics. It's extremely important, okay? And it has a lot of applications. So you have many strange things. Here, you can have 2 photons coming to a linear device, but the linear device will allow you to interact, having interaction between them and control the statistic. I think, I speak too much. So I will stop here, and next lecture, we will follow up with this again. We will go with the Beamsplitter, or I can give you an assignment. Assume that you have a Beamsplitter. You have n photons coming in. Okay? And this side is vacuum, is 0. Look what you will get. And the other homework, if you wish to just try, you have a squeeze light of alpha and zeta. See what you will get. And you will understand that squeezing is extremely, extremely sensitive to noise, which is here, is vacuum. Okay, these are your homeworks. I will stop recording, and then we can continue next lecture with follow-up. We will go with the coherency, and then Humphrey, Brown, and Twist, and etc. Okay.